Hey there. How are you?
Okay.
Yep,
Yeah.
got it. Okay, let's see. Sorry, I didn't get a chance to look at the things that you put in the content tabs. Let me take a look now. Um, okay, I could see, so I guess the ones that you put in red are the most you're having the most trouble with. Is that true?
hmm
Okay, so we can go over some of that stuff today.
I have a question though.
Yep.
Um, with the exam closing up soon,
Uh,
what do you think I should do at this point? Because I still haven't booked a test date.
oh, yeah, you should book a test date for like um if you still intend to take it this year, you could take it at latest September 13th. Um
But I don't feel like I'm ready based off of my scores remaining.
okay. So yeah, so after September 13, they'll uh I think in October they'll open um dates to take it next year with January being the first one.
I don't know. I'm 26.
So
I keep
you're
pushing.
you're way younger than you might feel or think.
It's just that it's just,
It's it's not a race. And whatever you do, you want to do like whatever will give you ultimately the best score and the best chance, to get into a school. But like, yeah, no, you're still young. There's lots of people who take it. I think like the average age or something. Let's see. I see average age is over 23. So, but yeah, that people like way older than you take it. Um, so yeah, I would say there's no absolute rush. It's okay.
so that means that there's a possibility I won't be taking this exam this year because my score is still 486. I haven't moved at all since May.
So let me see, because that was for whoops. That was the Altius score from July 11th. And it seems like that the CP section was mostly the issue there, but it's still higher than your AMC full length one score. So let's see. Okay, so yeah, we can knock out some like CP like physics concepts, and then let's have you take uh an AMC test next, just so we can like recalibrate. I know that you've done them before, but I want to see if this 480, because like the Altius tests are much harder. So let's see, like let's have you take for your next test one of the AMC tests. Um, and let's see what you end up getting on that one. If it's like, a 486 or lower, we can think about what we can do about that. But if it's like let's say like a 490 or something like that, I think we can manage to work with that for like the last month and a half.
Okay, I could
Oh,
do that. That's a plan.
yeah. So, um, and yeah, some of these physics concepts are like really like foundational, so understanding them will probably give you a much bigger results.
Yeah, I started off doing really good, but like I started also doing trying to get into like 30 questions a day per section.
Hmm.
And I did one in a physics thing.
Yep.
It's like you know the formula, but then I'm just not applying it. Like, of course, I know like the focal formula,
Yeah,
but
yeah, yeah.
I'm not applying it. And so, yeah,
Uh-huh.
so
That's a common thing. That's like most of the students that I get because most of the students uh that take the test aren't really like that into physics and it can feel like, okay, why do I need to know this? So, and also like physics is like cumulative. Like in bio, of course, you need to know like the cell and the organelles and stuff, but you can learn parts of the body and physiology and stuff like, separately, but in physics, they all like you need to know about vectors before you can, you know, move on to know about any of the other stuff. So yeah, you can knock out a good amount of this stuff. Um, what do you think?
yeah, let's do it.
All right. So first of all, let's talk about something like speed versus velocity. So let's say, or maybe I'll do distance versus displacement. So let's say that we have a, so let's say this is like a bird's eye view of a track, like a, that you can like run across, like run around, right? And let's say that this is the starting point and the circumference of this circular track, let's say, is, I'll just say like, so for the circumference is, let's say, 100 meters. Okay. So if you run like one lap, like let's say, can you see what I'm drawing?
Yeah.
Okay. So let's say that you start here and you do one lap. So you go, around and then you end up exactly where you start, right?
Mm-hmm.
So the distance that you traveled would be just that length of the track, right?
Okay.
So 100 meters, right?
Yeah, because that's the what? The circumference of the circle? The 100
Yeah,
meters? Okay.
yeah. But like it doesn't have to necessarily be that. Like let's say that, let's say that you're going this way from here, start, you go here, and let's say the distance here is also 100 meters. If you run to this side and then you run back this way, what's the total distance you've run?
Distance is what? Dependent, so 200 meters?
Yes. Yes, yes, yes. So now that's something called a scalar, which means that it's a quantity that just has a magnitude, but it does not have a direction.
Mm-hmm.
Okay? Now, let's say that we have the same circular track, or this time I'll make it in blue. Whoops. No. Okay. So, same circular track, but now we're going to figure out the displacement And displacement is kind of like distance. However, it is a vector, which means that it's going to have, in addition to a magnitude, it will have a direction. And we can indicate direction by using arrows. So you can think of this as when you run when you run this lap, you're going to go in this direction up and then this direction to the right, then this direction down, this direction to the left, and then this direction up, like that. So now when we use numbers, we can indicate direction by making, let's say, if we make the up direction positive, then the down direction will be negative. So let's say this distance up, let's just say is plus 50 meters. And then let's say we go, well, maybe I'll make the math right because this would be like 25 meters, let's say. And then let's make if we go to the right, also a positive number. And let's say that that's 50 meters. And I'll actually make this one like two things like that and like that. Now, when you get to this point over here, you're going to start running down, right? Like over from here.
Mm-hmm.
So now this down arrow here is identical to this up arrow in magnitude, but it will be in the opposite direction. So we can just indicate that in numbers by making it a negative sign. Let's make this negative 25 meters. And then from here down to the bottom, let's make that another negative 25 meters. And then when we are here in this bottom right corner, you're going to be moving to the left. What number do you think we'll put for that?
-15?
Yep. And then from here back to the start,
Oh, just positive 25.
from here to here, what number should we put?
25.
Positive 25, right?
Mm-hmm.
So now if you run this lap, what will be your ultimate displacement?
Would it be 0?
Yeah.
Okay.
So let's say that you're running on a treadmill, right? You can run a bunch of miles if you're measuring it in distance, right?
Mhm.
But if you're measuring it as displacement, you wouldn't be increasing your displacement, right?
No, because you're staying in one place.
Exactly. So that's the heart of what a scalar versus a vector is. A scalar does not take into account direction, but a vector does. And therefore, your scalar, and since we indicate direction by using like a positive and negative,
Hmm.
your scalar values will only be positive, but your vector values can be positive and negative.
Okay.
So now, um, so another example of that is speed versus velocity, okay? Where speed is a scalar and velocity is a vector, right?
Okay.
So if you're driving a car at constant, let's say, speed, like let's say it's like 30 miles per hour,
Hmm.
and then, you make a turn, when you look at the speedometer, right? Let's say that it stays constant at 30 miles per hour. And that's because the speedometer, or whatever it's called, odometer or something, I don't really drive. Um, it's only gonna be able to read, like the car doesn't know um how to measure velocity. Like it's gonna, if you're driving at 30 miles per hour and you make a turn, the car is still gonna, and it's at the same speed, the car is still gonna say 30 miles per hour. And that's because your speed isn't changing, but if you are turning, your direction is changing, which means the vector would change, which means your velocity will change, even if your speed doesn't.
Okay.
So now, let's say that we have, say we have like a ledge with a cannon here, and this cannon is going to be shooting some cannonball at some angle. Um, let's say this angle is theta. Let me extend this. Whoops. Let's say that this angle, as we measure it from the horizontal being just flat to the right, and vertical just being up straight,
Hmm.
this angle theta is going to be, well, it's going to be a vector. And if we wanted to actually like do something with this, like let's say we wanted to figure out how high this cannonball is going to go, how far it's going to go. So if we wanted to figure out how high it's going to go, we're going to concentrate on we're, well, first of all, we can take a vector and we can break it up into a horizontal and vertical component. So this, we can, I'll use blue. Whoops. So this is going to be our horizontal, or let's call it the x direction velocity. So I'm just going to write v with a subscript x, and then this arrow going up is going to be the vertical or y velocity. So v with a subscript of y. And then the actual v is going to be the actual, cannonball direction like that. So what we're going to do here when we break a vector into its horizontal and vertical components is we essentially use you remember like SOHCAHTOA?
Hmm.
So we
I
can,
got I got a thing for that too.
yeah,
I got an acronym for SOHCAHTOA to know like sine 30 and cosine 30. It's like 1970.
okay, okay. So if we just had, so I'm gonna go on the left for a sec, just to draw that triangle with theta here. Like this is the hypotenuse. Let's say this is, or I'll just call it V, and this is Vx, Vy. If we wanted to solve for Vy, how would we set that up in terms of SOHCAHTOA?
You said VY?
Yeah, so Vy is the that vertical component, and Vx is the horizontal component, and then regular V is the actual well, in
For
this case,
hypotenuse, so
the hypotenuse.
we're
Yep.
looking at sine.
So you said sine, yep, is equal to.
VY over V. I mean opposite over yeah, VY over V.
Yep. And so now we can just multiply both sides by V to get Vy is V times sine of theta, right?
Uh-huh.
Now, what do you think Vx could be?
VX is cosine, so the same thing. VX over VY.
Yep. So we
V,
can
mm,
do V cosine theta, right? Right? Does that make sense? The V.
yeah, like I know how to do this. I think the question was more so about like people running around and it wanted me to know what the displacement was. Like it was like it went this way, this way, this way, this way. So what is it the place displacement? And I didn't remember that it was independent. I mean, I didn't realize. Yeah, I remember it was independent.
Okay. Oh yeah, so I see that you put in
Highlighted.
red vector addition.
Yeah.
So like if you were to so what I just showed is like the backwards of vector addition, like when you take a vector and you break it into components. But let's say you had a vector like let's say this and and I don't know, like this. What you do is you do like something called tip to tail.
Mm-hmm.
So let's say this is +5, let's say this is +6. You could take either of these like let's take the +6 vector and we can take the tail end of it and put it on the tip of the 5 vector, and then you just solve for the hypotenuse, which will then be
Pythagorean theorem.
mhm. And then your hypotenuse is going to be the vector sum
Mm-hmm.
of these two vectors.
All right.
Yep.
I do need help with I think the second part of the highlighted and acid-base chemistry. So the second part in acid-base chemistry.
See speed, velocity, average, and instantaneous.
No, not those.
Torque, torque lever arms.
Yeah, and then like that section with potential kinetic.
Yep. Okay. So in order for me to talk about torque, let's first talk a little bit about work.
Hmm.
So work is FD cosine of theta. And when you see a cosine term in like an equation, um, what that implies, because cosine of 0 is 1 and
Hmm.
cosine of 90 is 0, right?
Hmm.
Sine of 0 is 0. Sine of 90 is 1, right? So let's say we have a box that you apply this horizontal force to, and it moves this distance. What's the angle? Sorry, it's not as exactly straight, but what's like the angle here between this force and distance?
The angle
Yep.
isn't it like going the same way? Yeah, so there is no angle.
Yep. So that'll be an angle of 0, right?
Hmm.
And that's because the force and the distance here is parallel, right?
Hmm.
So this FD cos theta is maximized when the angle is 0. So I could also rewrite this as FD, and I put a little subscript here. So the subscript there is it doesn't mean 11, it means parallel.
Hmm.
Okay. So if you were to have a force applied directly down like this, what would the work be in this case?
Like what? Because it's at a 90-degree angle.
Hmm.
Okay. It would be 90 degrees, I guess. Is that what you're asking? Because of the hold on.
Hmm.
Yeah, because of the angle that it's at right now, because there's a force going down and a force going left.
Okay. So the angle is 90, and then what would the work be?
Oh, like what is the work being done onto it? Would it also be like, no, it'd still move. It wouldn't be zero. That would be zero because it's a force pushing onto it and a force pushing at opposite areas.
So the angle is
The opposite.
90, and that
Uh,
means the cosine 90 is 0, right?
yeah.
So if your force is perpendicular to the direction that the object is moving,
Mm-hmm.
doing no work.
Yes. Okay.
So now that we talked about that, torque is just like work, except we have a sine term in there.
Yes, sine. Yeah, it's FR sine. Yeah.
And what that means is, so let's say we have something like this. I put a circle on the left. So this is let's say this is like a door. And the circle on the left is just to indicate like a hinge. And then the distance here or the length of the door we can call R. And let's say we apply a force in this direction.
Mm-hmm.
The angle is what?
Rotating.
No, so the angle between the force and the R.
R, yeah, it's still like a perpendicular one, but
So angle is 90, right?
uh-huh.
So your sine term would then be.
It will be sine 90, which is what, one
Mhm.
at
So we
home?
could rewrite this as this, and I put a subscript there to indicate perpendicular,
Mm-hmm, mm-hmm.
and that'll be torque. And yes, it's going to produce, and that's why we call the distance here R, because it's going to produce a rotation with this R value being the radius of that rotation. Okay?
Okay.
So work and torque are super similar, except work is when your force and distance are parallel. Torque is when your force and distance is perpendicular. So that also means when you have maximum work, you have minimum torque. And when you have maximum torque, you have minimum work. So if you're opening or closing like a regular door, how much work are you doing?
You're doing minimal torque to open the door, so mass work.
So, sorry. So when you open
Opening the door to me doesn't require a lot of work. Oh, so
one,
then minimal work, mass
it's
torque.
like it's weird because like in physics,
Yeah.
it's like it's like if you hold a heavy weight, it feels like you're doing a lot of work, but technically, if that weight isn't moving, it's not
Mm-hmm.
going to be work. But if you're opening a door, right, that's like has a hinge,
Mm-hmm.
you're doing actually zero work because the door handle that you are like pulling or pushing
Mm-hmm.
is perpendicular to the length of the door, right?
Yeah.
And if
Oh,
that's
yeah.
perpendicular, yeah,
So when you open it, it's oh, okay. So it's zero.
yep. So yeah, so regular door would be zero work, but some type of torque. And then let's imagine you had like a sliding door.
Mm-hmm.
Would it make sense that opening and closing the sliding door would be zero torque, but some type of work?
Yes, because parallel is one for work.
Mhm. Good. And so like, if I turn this page,
Mm-hmm.
I'm doing work or torque.
Parallel. You're doing torque.
Good.
Okay. I
Hmm.
did not look at it that way. Oh
Yep.
my gosh, make acid base make sense.
So, um, let's see. So there's like three definitions for that, right? There's like the Arrhenius definition, which is like the most simple, and
Mm-hmm.
that's where an acid just produces hydronium ion, which is essentially just water getting protonated,
Mm-hmm.
and the a base produces whoops, hydroxide ion, which is just water being deprotonated.
Mm-hmm.
Now, when on the MCAT, when they say an acid or base and they don't specify, the default is the Bronsted-Lowry definition,
Okay.
and that is going to be our default definition for acid and base. So an acid in this case is a proton donor, and like H plus is a proton. And a Bronzolari base is a proton acceptor. So for example, if I had HCl, that'll just dissociate into H plus, Cl minus. So it's producing H plus or like donating H plus. And a base could be like NaOH, which can dissociate into Na plus and OH minus. And if these were mixed, you would have the OH minus get protonated by the HCl. Or let me put it in okay, let me do it in terms of like an amino acid. Let's do like okay, I just drew like the skeleton, like the basic, um amino acid. So this like is essentially like an amine here.
Mm-hmm.
Um, and this is going to act as a Bronsted-Lowry base, and then this carboxylic acid is going to act as the Bronsted-Lowry acid. So,
Yeah. Proton is 15.
what is the Bronsted-Lowry acid going to do?
They're proton donors.
Yep. So it'll donate a proton, which means it'll lose a proton and be O minus over here.
Mm-hmm.
And the Bronsted-Lowry base is going to accept a proton, right?
So that'll be NH4.
Yep. And this is something they call a Zwitter ion.
Mm-hmm.
And that's like Zwitter is like the word in German for like hermaphrodite. So we can call this a Zwitter ion because it has both that acidic part and basic part.
Mm-hmm.
And yeah, so that's bronzolaric acid and base. Um, what
What did I need help with? I more specifically needed help with the pKa pH portion,
okay.
like, because I got like how to do like the MCAT math, and like if it's less than pKa, it's acidic. Conjugated base, conjugated acid. That just that.
Okay. So so here I'll do this.
Yeah.
So when that acid donates its proton,
Mm-hmm.
like the version of it that's already given its proton away, this is now called the conjugate base.
Mm-hmm. Conjugated base.
And Now let's say this ammonia is our base that accepts a proton. The version of it that has that proton, that extra proton, is now called the conjugate acid.
Okay. Yes.
So another way that they can write it is like the acid could be HA in caps, and then the conjugate base can be the A minus, and the H plus is just the H plus.
So for like something like H2PO4 plus NaOH, um, equilibrium sign.
Maybe you mean H3PO4?
I think it's H2SO4.
Okay.
Am I right? Am I wrong?
Yep. You could have
No,
H2S.
H3 is and H3PO4.
Okay.
I got two on here, so you're probably right.
So,
NaOH equilibrium sign H3O plus NaPO.
so, so for a polyprotic acid like
Mm-hmm.
this is going to be this could be a little bit here. So I'll first just explain with this triprotic acid. So let's say that you start with the H3PO4 and it loses one proton.
Mm-hmm.
You then have H2PO4 minus plus H plus, right?
Mm-hmm.
So we could say this is the acid and this is the,
Conjugate base.
yeah. Now the thing is, oops. Okay. Now the thing is, with polyprotic acid, since we defined our acid as a proton donor, and in a polyprotic acid, the acid has more than one proton, it can donate. So the conjugate base here, H2PO4 minus, could act as an acid also by donating another proton. So I'll use blue here.
Also, now it can further act like an acid.
Yep. So I'll
And
do it
then,
like this.
mhm,
Turn into HPO4 2 minus plus H plus. So now this could be, oops, conjugate acid, maybe I'll just say 2. And then in green, I'm going to make it also, ooh, sorry. Hold on. Sorry. So conjugate base here can act also as another acid because it has one last proton that can donate.
mhm,
And then that can turn into PO4 3 minus plus H plus. And then this would be conjugate base 3.
mhm.
Oh, and then this would be conjugate base 2. So, so yeah, for a polyprotic acid, the conjugate, when it loses its first proton, the conjugate base can act as an acid as well.
Okay. And then conservation of energy and work theorem. I think they go together.
Uh-huh.
Yeah.
So, did you have a question about like pH and pKa as well?
I mean, I know what it is and I know the formula and I learned some like little MCAT math for that ish in a way. Like she
Uh-huh.
taught me that I could use, so if I could use pH equals pKa plus the log instead of doing the whole ice thing because I needed a way to simplify it, she said use negative log. She told me to use an equation that I just got to memorize.
Uh, so the ice tables you don't have to do because like they're not going to give you a value of like X or the change that is going to
Mhm.
be uh non-negligible, but the idea behind pKa versus pH is so let's say that this Zwitter ion, so a pKa will be um, an intrinsic property of that molecule, and a pH could be, let's say, like, so that's what I was drawing. I drew like kind of like a container here. So let's say that we took this amino acid Zwitter ion with some pKa, and then let's say that this we have a container that is of a pH, and we dropped the amino acids with our ion into this container that has a pH. If
Mhm.
the pH is larger than the pKa, you can think of it as,
Base.
yep, the environment is going to be relatively basic, which means that the amino acid here is going to be deprotonated, right?
Yes.
So I'll just write amino acid gets deprotonated, turns negative. And then if pH is less than pKa, it'll get protonated, turns positive. So that's that. And then for the calculation, so if pH is negative log of H plus, we can do two shortcuts. So if you're given, let's say pH is 6,
Mhm.
then you can do and let's say you're solving for H plus concentration. You could just take that pH value, take 10 and put it to the power of negative that pH value. So if your pH is 6, your H plus concentration would be 10 to the power of -6, right?
Mhm. Okay, yeah. Your pH is 10 to the -6 since pH is 6.
Yep. So if you're given a pH and you need to find the H plus concentration, you could just take 10 to the power of negative pH. Now, the other way around, let's say they give you H plus concentration is 1 times 10 to the, I don't know, let's say third power. What you can do is you take this exponent 10 to the power of 3. You take the exponent only, which is 3. You flip its sign. So let's say we have, so let me do it like this. So let's say that we have H plus concentration, essentially 10 to the power of -3. So your pH could be you take the exponent and you just flip the sign.
Oh, it's -3 now?
So I changed it so that we start off with 10 to the power of -3.
Okay.
So now it'll just be +3.
Mm-hmm.
And then you subtract it by the log of this first number. I'm going to make this number 2. And I'll show you like a shortcut for that as well. Since log of 1 is 0
Mm-hmm.
and log of 10 is 1, the log of any number between 1 and 10 we can approximate as 0.5.
Mm-hmm.
So if we have a concentration of 2 times 10 to the -3, we take that -3, we flip the sign to get 3, and then we subtract it by log of this first number here, which in this case is 2. And if that first number, if it's in scientific notation, is going to be, something between 1 and 10, and we can just approximate that as 0.5. So this turns into 3 minus zero point 0.5, which is just 2.5.
Okay.
Yep. So yeah, that should cover pKa, pH, and the calculations. Um, all right, and then you said the conservation of energy or the work energy theorem.
Yeah, conservation of energy and work energy theorem and like how they're like they were just closely related. I just didn't know that I believe potential energy is a part of the equation as well. I didn't know that potential energy was negligible and that I would be just subtracting the change in kinetic energy.
Yeah, so first I wrote, so in physics, the definition of energy is the ability to do work. And that's why in the work energy theorem, we essentially have work being equal to energy, and energy can be kinetic energy, which is if something is moving,
Mhm.
and that is 1/2 mv squared. And you can also have potential energy. Now, there's different types of potential energy. You can have gravitational potential energy.
Mhm.
So I usually write potential energy as a capital U,
Yeah.
and the subscript will indicate the type. So if you had gravitational, it would be U subscript G is equal to mgh. So that's for gravitational. You could also have elastic and electric potential energy.
Mhm.
And for these two, or you could also have um sorry, this would be like in a capacitor. So for these two, the formula is going to look kind of like the formula for kinetic energy. So elastic potential energy, I'll write U subscript E, and this could be 1/2 kx squared, and you can kind of see how it's similar to the 1/2 mv squared. And the potential energy that can be stored in a capacitor is 1/2 CV squared, and this time the capital C is capacitance, and the capital V is voltage.
Okay.
And total energy is going to be the sum of, if some potential, sorry, some kinetic energy plus some type of potential energy. So if we're dealing with like gravitational potential energy, this could be like, 1/2 mv squared plus mgh. And when it comes to oh, and then we could say like, okay, work is equal to that. So we can say, basically this. And okay, and then let's say that we have another ledge, and this is you, and you're holding a ball up here, and this ball is this height from the ground. And here, right before you drop it, okay, so what we're gonna do is, for conservation of energy, I'm gonna do initial kinetic plus initial gravitational is equal to final kinetic plus final gravitational. So when the ball is up here and you're still holding it, what is its kinetic energy?
What is kinetic energy?
For the so like you're holding a ball.
Oh, what is the kinetic energy as you're holding the ball? Zero?
Yep. And the gravitational potential will just be mgh.
Mm-hmm.
And then when you release the ball, it's going to start to fall. And as it
Mm-hmm.
starts to fall, it starts to gain kinetic energy.
Mm-hmm.
But as it starts to fall, since the height is decreasing, it's going to be losing gravitational
Potential.
potential, right?
Yeah.
And right here, right as it hits the ground, its height is 0, right?
Mm-hmm.
So its final gravitational potential energy will then be 0.
Mm-hmm.
And its final kinetic energy, which I'll write is 1/2 mv squared, will equal its initial gravitational potential energy. And so I showed like initial and final, but in between, what happens is, like, as the ball falls, it loses gravitational potential, but it gains kinetic. So you essentially have, as it falls, so if I were to draw like maybe a graph, like let's say time, kinetic energy, and then time, gravitational potential, your gravitational potential is going to start to drop, and your kinetic is going to start to rise.
Mm-hmm.
Yep. And we can tie in work here by saying the Earth is doing work on the ball as it falls.
Yeah, yeah, I had to learn that too.
Mm-hmm.
So I had a graph where, I mean, yeah, it makes sense. Never mind, it makes sense.
Tell me about the graph.
It was just it looked like that, but then it leveled out. So actually, let
Oh,
me
okay.
get that. But it's still the same formula where all I had to realize was it was work energy theorem, where I just took away final from initial.
Mm-hmm.
But initial was zero. At the end of the day, initial was still zero. And then all I had to do was solve it. And I just didn't know that that's what, but, and honestly, I didn't even know that's what I needed to do anyway.
Okay.
But yeah, I had to learn that. Yeah. But that's it.
All right. Awesome. So let's see. Oh yeah, so we covered potential energy with MGH and then the 1/2 KX2 for the spring. I wrote that here as elastic. And
Hmm.
I guess they didn't write it up here, but they would have written it down where they talk about capacitors, but that would be the potential energy in a capacitor. So yeah, overall, when it comes to these concepts, try to like just, you know, for like the next day or two, just like in real life, think about so like it's kind of nerdy, but like when I think about it, it's like when I go into my apartment building and I climb the stairs, I'm I'm doing work and I'm gaining gravitational potential energy as I go up the stairs.
Hmm.
And when I'm like opening a door, like I'm doing torque. So like with these concepts, like yes, there's the equations and there's all of that stuff, but with like the physics concepts, they're there to like explain how things work like all around us. So if you can have a really, really um intuitive grasp of these concepts, it's going to really help because everything is ultimately physics. Like even if you have something in biology, or like the way a cell works, ultimately like it's still going to be, things moving, things involving energy. So if you can just have a very, very good intuitive understanding um of this stuff, it can really help.
Would help.
Yeah.
Um. Okay. Yeah. I'm just gonna keep answering questions and reviewing them.
Hmm. Cool. So I'm going to export this as a PDF and I'm going to send it in an email to you.
Okay. Yeah.
And yeah, so now, okay, so hopefully this was helpful um and yeah, you're doing everything right. Like, from highlighting this stuff in the content tab so we have something to go over. And yeah. Oh, and
And
then again.
all I've been doing is answering questions
Mhm.
based off of the sections. It says
Yep.
like I need to work on. So that's literally all I've been doing: answering, reviewing, answering, reviewing.
Okay. Okay. Awesome. So yes. So I guess the next test you take, just take like an AMC one, and then
Hmm.
we can get some type of like new base.
Understanding where I'm at. Got you.
Yep.
All right.
All right. Awesome.
Soon.
Good seeing you, and I'll see you next time, okay?
Okay.
Take care.
Okay. Bye bye.
Yeah.